again, introduce your major and your project. Thank you. Welcome, Nick.
Once again, my name is Nick Pfister. I'm working in the computer security lab under my mentors Fish, Christoph, and Jan. Fish is here today, thank you very much. Under faculty advisor Christopher Krugel, and I'm working on a visual approach to symbolic execution. As many of you well know, we live in a very modern era where devices all around us use some sort of computer software. And a lot of these devices take for example a power plant, an airplane, or a medical device, can be very safety critical. So if this software could fail, if it could have some sort of vulnerabilities, say for example a power plant could stop working, an airplane can crash, these are things we really want to avoid. So what we want is some type of analysis so we can analyze this software, scan it for different vulnerabilities, see how it works, and also determine the potential for this software to be malicious, which in that case we would call it malware. So why are we using symbolic execution? So there's two types of analysis. The first of which would be dynamic analysis. Dynamic analysis basically runs a program many times, each time sending a different input. Now, say for example, if we have a test program that says input x, if x is equal to 42, it goes one way, and x is not equal to 42, it goes another way. We could keep sending inputs until we eventually find that this program could go either this way or this way. The problem with dynamic analysis is if you think you're just sending more and more numbers, it's really hard to cover the entire breadth of the program. There could be certain branches of it that you're missing and you're not covering. So then we also have something called static analysis. Static analysis, instead of running the code, actually just examines the source code of the program. And symbolic execution is a part of static analysis, where what we're doing is instead of running the program, we're virtually running it, and we're sending a test input. For example, we could say x is equal to s. And so when x goes down this branch, we can use a constraint, what we call a constraint solver. And this is really just more complex mathematics that would be going through and solving, okay, so for this branch, what would x have to be equal to? And we find 42. So the big advantage to this is it's a lot easier to cover the entire breadth of the program. We can see our entire scope and exactly what the program is doing. So since our whole goal with symbolic execution is we want to understand how the program works, we want to see all of the different branches in it, it would be incredibly useful if we had some sort of tool to visualize this. And in computer science, we have what we call a control flow graph, which is really a way of visualizing software as a collection of different functions. So this would be an example of an empty control flow graph. So each box would represent a different function in our program. And then the lines connecting each box would represent where each function can lead to for different inputs. So this would eventually draw out our entire line of code. So we would like to create these to help analyze the results for our symbolic execution. So each box will contain useful information about how that function works, what's the data being manipulated in each one. Of course, we'll have these lines connecting the different functions to show the control flow, which is basically just how each function leads to other functions. Of course, we want this to be very interactive. This is really a tool for analysis, so the more interactive it is, the better the user can see exactly what's going on, and the better we can assess the security of a program. So our objectives. So we have our symbolic execution system. That's what our entire group is working on. That's the bigger project. And so what I'm working on here is our front end, what we would call the front end. This is going to be the visual end. This is where the graphs are being drawn. But the problem with the front end is this is not actually doing any sort of analysis. It's really just a visual platform. So in addition to creating the front end, I also need to create some sort of a connection to extract data from the back end and handle user input so we can connect these two and turn this into something that's actually useful. So the first step that we take in creating this visual platform is we need to identify and evaluate useful libraries. For those of you that don't know, in computer science, a library is really a collection of different code. A great analogy would just be a physical library. You go into the library, you select what books you want, and then you go and you read those books. So we go and we find these libraries and we select the code in it we need for our purposes. So we really don't need to reinvent the wheel. These libraries already exist. So an important part is identifying what libraries already exist and determining what works best for our application. So for example, just to kind of go through this process, I came across probably about 50 different visual libraries. I narrowed it down to these two, and the way I was able to determine which one works best for our applications is simply, we've got Graph Dracula and we've got JS Plum. The problem with Graph Dracula is it doesn't work on all modern browsers. So that would be a big problem for usability if someone was to say log in on Safari instead of Google Chrome and it all of a sudden doesn't work. So that was an easy way to eliminate it. So once we've selected our library, so now I've got JS Plum from the previous slide that I was showing you, we need to implement it. This is where you're, say, back to our old analogy, you're going to the library, you're selecting what code you want, and now you're going to apply it for what you need. So really, this is just a collection of different ways to make graphs, and I want to select what I need to turn it into a control flow graph that would look sort of like this. Then in addition, we want to use a similar process of finding libraries to create the connections between our symbolic execution system and our front-end interface. So that will be the next step, and that will be the same sort of means in which we selected these libraries. So when we're considering experimental data for a visual application, it's a little bit of a tricky subject to tackle, but we can narrow it down to two different things we can measure. That would be the speed and the usability. So I ran a couple tests on a very basic program being input and drawing graphs of it, and our average loading time was 5.15 milliseconds, very little variation in the tests. And so, of course, if you're just clicking on a page to open up in Google Chrome, you're never going to notice this. So first, this is really something that's going to be negligible, especially considering that there's going to be work going on in the back end, which is going to take much longer than this. So this is going to be negligible. But we also do need to consider that as we improve this program to handle much more complex graphs, this may need to be reassessed because it could start taking a lot longer for it to load. So what's really important is we need to examine the interface. We want to examine the usability of our program. So here is a snapshot of one of our earliest revisions of the interface. See, it's running on Google Chrome. And of course, our goal is for it to be user-friendly and easy to understand. So let's see if it's doing that. Well, first problems, as you see, it's very hard to see where each connection is leading. See, these are sort of intersecting with each other. These containers are relatively small. There's no information in them. They're not resizable, not very user-friendly. So one of the very first revisions I did to kind of solve this connection error is I actually allowed the user to click and drag these boxes. So instead of like this, where they're just drawing like that and there's nothing you can do about it, now you can reorganize it. Now you can see the connections behind it. This is good, but the problem is we don't want the user to have to handle this every time they log on. It's going to, in the end, turn out to be a waste of time. And also, these are still lacking information. So after our final revision, or our most recent revision, there'll still be more, I came up with some more improved way to visualize these connections. As you can see, there's multiple stemming from each box. So it's very clear. You can see that this function leads to this function or this function. And these resize, everything fits very nicely. But the really important part to think of is the graph organization. Whereas instead of having the user have to reorganize this for it to look right every time, we're actually having algorithms that you can kind of think of how would you draw a flowchart like this in real life? What's the logic behind it? So now I'm writing computer algorithms that actually think of that logic behind it and draw it. So now we don't have to have the user rearranging things. So since this is part of a much larger project, and that's a project on symbolic execution, this is going to continue to be improved. Currently, this code is being used by other researchers in the SEC lab. It's being implemented to visualize control flow graphs. And we're going to be using this at the upcoming security conference, DEF CON, which we're going to this weekend, which we're all very excited about. And additional revisions are going to be made for this, so it can start. I started to lead on this earlier, but we also want this to handle much larger graphs, much more complex programs, and make sure it still does that within a reasonable speed. So, on a more personal level, the achievements involved in this entire thing. I'd like to point out that before I came here, my computer skills were Java, C, C++, fairly basic programming languages. However, to create this interface and to end up producing this, I had to first learn HTML, CSS, which is really for the layout, the styling of the text pages. So how do these boxes look? How's the page laid out? JavaScript and jQuery, which is a library of JavaScript, which is how we generated the graph. That's how we came up with the logic behind it, as well as Python, which is what we use for the back-end development, and Git and GitLab, which is an extraordinarily helpful tool we use in computer science, which sort of allows us to create big projects and share our code and merge our codes with our other collaborators. So as you see, this over doubled after the end of this project, which was very exciting for me. But most importantly, I also learned the sort of organization and planning that involves such a large project like this. And of course, the different methods that can be used to overcome the different problems. And of course, trial and error. This would not have been, yes, Thomas Edison. If I have not failed, I've just found 10,000 ways that it won't work. If I came in here, sat down, and wrote everything out in a week, this really wouldn't have been so worthwhile. It was going in and overcoming the different failures that happened in this that really made this such an exciting experience for me. Thank you very much.